Here is 1 kilojoule of energy. And here is another. 1 kilojoule stored in a lump of burning coal at 1500 degrees. 1 kilojoule in a puddle of water, slightly warmer than the room. The first law of thermodynamics insists these are equal. 1 kilojoule is 1 kilojoule. And yet you know these are not the same. You could run a power station off the coal. You could run absolutely nothing off the warm puddle. Same energy. Completely different worth. The first law counts energy. It cannot see quality. To measure what energy is actually worth, how much useful work you could truly extract, we need a second quantity. It's called Exergy. And once you can see it, you discover that in almost every machine we build, most of the potential is destroyed before it ever does anything. This is about the energy you can never use, and exactly where it goes. Exergy is the maximum useful work you could extract from something as it comes into equilibrium with its environment. Work is only possible when there's a difference the environment doesn't already have. So Exergy is always measured against a dead state, the surroundings, at temperature T0. Take heat at temperature T. The most work any engine could ever extract is set by Carnot. The useful fraction is 1 minus T0 over T. Watch what that does. Heat from a flame at 1600 Kelvin, 81% convertible to work. Steam at 600 Celsius, about 66%. But heat at 45 degrees, just above the room? 6%. The same joule is worth 13 times more at the flame than at the condenser. Energy degrades in quality, and quality is temperature's distance from the dead state. For a flowing stream, we write it exactly. The flow exergy psi equals the enthalpy difference from the dead state, minus T0 times the entropy difference. Hold on to that second term, T0 times entropy. Every time entropy is generated, that term grows, and exergy quietly disappears. That is the whole story of this video, in one term. Now a real power plant. Steam boiler at 15 megapascals, 600 Celsius. Turbine. Condenser at 10 kilopascals. Pump. A textbook Rankine cycle, with real steam properties throughout. First law accounting first. For every kilogram of steam, the boiler adds about 3,400 kilojoules. The turbine delivers roughly 1,277 kilojoules of net work. The condenser dumps the rest, 2,100 kilojoules, into the cooling water. So the first law hands you this. 38% becomes work. 62% is thrown away at the condenser. Look at that giant red bar. If you'd never heard of Exergy, where would you attack? The condenser, obviously. 2/3 of your energy, pouring into a river. That instinct is almost completely wrong. To see why, we stop counting energy and start counting worth. Same plant, same kilogram of steam, but now we track Exergy, the actual work potential, through every component. The heat arriving from the furnace at 1600 Kelvin carries about 2,747 kilojoules of Exergy. That is our budget. The most work we could ever get. Let's follow it. The turbine converts Exergy into shaft work, 1,277 kilojoules. Against our budget, that's a second law efficiency of about 46%, already different from the 38 the first law reported, because now we measure against what was possible. Now the destruction, and here is the moment. The single biggest loss is not the turbine, not the condenser. It's the boiler. Pushing heat from a 1600 Kelvin flame into 600 degree steam destroys about 1,169 kilojoules, 42% of everything you started with. The boiler destroys nearly as much potential as the whole plant delivers as work. Why? That second term, T0 times entropy generated. Every time heat leaps across a large temperature gap, from flame to steam, entropy is generated, and T0 times that entropy is exergy, gone. The first law is blind to this. It calls the boiler 100% efficient. Exergy sees a massacre. The turbine's irreversibilities destroy about 6%. And the condenser, the villain the first law told us to attack? 5%. 5. Here's the reconciliation. The condenser does reject 62% of the energy. But that heat is at 45 degrees, right against the dead state, so its quality is about 6%. You're dumping an enormous quantity of nearly worthless energy. Attacking the condenser is like chasing a flood of pennies while someone empties the vault upstairs. And it all closes, exactly. Work delivered, plus every kilojoule destroyed in every component, equals the exergy we started with. Nothing vanishes from the energy books. But on the exergy books, more than half the potential is destroyed before the plant does a single useful thing. So the math has redirected us. If you want more work, don't chase the condenser. Shrink the exergy destruction in the boiler, the biggest block. And exergy tells you exactly how. Close the temperature gap that heat jumps across. This is why every efficiency move targets that gap. Higher steam temperatures and pressures, supercritical boilers, pull the steam closer to the flame. Reheat. Regenerative feedwater heating, which preheats the water so the coldest, most destructive part of the jump is avoided. Everyone is, underneath, an attack on T0 times S-gen. First law efficiency asks how much energy came out as work. Second law efficiency asks, of the work that was possible, how much did you get? Only the second question can be answered wrong in a way that costs you. Only the second tells you where to look. Back to where we started. 1 kilojoule in the coal, 1 in the puddle. Now you can say precisely what separates them, exergy. Work potential, measured against the dead state. The coal's kilojoule is almost all exergy. The puddle's is almost none. And you've seen the truth the first law hides. In every real process, exergy is destroyed, never created, every time heat crosses a temperature gap. The energy is all still there. It has simply been demoted to a temperature so close to the environment that no engine can ever touch it again. That is the energy you can never use. The first law tells you energy is conserved, and it's right, which is why it can't tell you what to do next. The second law tells you quality is destroyed, and points at the destruction. If you take one idea from this, don't ask how much energy a process uses. Ask how much exergy it destroys, and at what temperature gap. That question has an address. Derive everything. Trust nothing you can't derive. See you in the next one.